So in this video, I want to talk about one more last example, one more test we can use to calculate residues. And that's going to happen when you have f as g over h, where g is non-zero at z naught, and where h has a 0 of order 2 at z naught. So in other words, h of z and h prime of z naught are both 0, but h double prime of z naught is not 0. So that means you can factor out a z minus z naught squared from h, and then you're left with a function that's non-zero at z naught. And if that's the case, then your residue has this formula. And this formula, what I said before was true about, in general, if you have a polar order k, you can multiply by z minus z naught to the k, take k minus 1 derivatives. The problem with that is that when k gets large, the calculations get kind of out of hand and almost unbearable. They're all true, of course. I mean, we prove this. But in this case, even if you have some function that's as innocent looking as 1 plus z over 1 minus cosine z, even then the algebra gets way out of hand. So this formula will be tricky to deal with kind of this case. Okay, and that's when we have, this is again a double pole. We have a pole of order 2. And so this is our formula. So the residue is going to be 2 times g prime of z naught over h double prime of z naught minus 2/3 times this quantity. So g of z naught h triple prime of z naught divided by h double prime of z naught quantity squared. So that's what we're looking at. We're going to apply the residue theorem. The only places where 1 minus cosine of z is going to be 0 is when cosine is 1. That'll happen at 0, and then plus or minus 2 pi, plus or minus 4 pi, and so on. But if we're restricted to the circle of radius 7, then the only values where that'll happen is at 0, 2 pi, and negative 2 pi. So we just have to compute 2 pi I times the sum of those residues. And so that's what we need to do. And so if we look at the residue of f at 0, we're just going to use this formula. If you use the formula where you have to compute phi and then you multiply by z squared and then you take limits, you get derivatives that get out of hand really, really quickly. And L'Hopital's rule just doesn't help all that much. So it's still true that if you could calculate the limit that way, you would get the residue, but it's just that when you do that limit in practice, it's a little bit untenable. So it gets kind of out of hand. So let's compute this residue. Okay, so this is the first one. So the residue of f at 0, just again, notice that we're exactly in this value. If you take g is 1 plus z and h is 1 minus cosine of z, then notice that the denominator is 0 at 0, because you get cosine of 0 is 1. The derivative is sine, so that's also going to be sine of 0 is 0. And then the second derivative is cosine, but cosine of 0 is 1. So this is where the first and second, the original function and the first derivative are 0, but the second derivative is not 0. And then we can just apply the rule that we have. So notice that to do this, we just have to know that if g, so if g is 1 plus z, that means that g prime is just 1, so no mystery there. And if h is 1 minus cosine of z, then h prime of z is going to be sine of z, and therefore h double prime is going to be cosine of z, and h triple prime is going to be negative sine of z. Okay, so again, no big mysteries there. Okay, so that's the deal there. Now let's look at what each of these are. So what's g prime of 0? So g prime of 0 is going to be 1. G prime of anything is 1. And h prime of 0, I'm sorry, h double prime of 0 is going to be 1. And h triple prime of 0, notice that that's just going to be negative sine of z. So at 0 and then plus or minus 2 pi, h triple prime is going to be just 0. And that means that the residue is really just going to be this part, right? 2 times g prime over h double prime. And so the residue of f at 0 is going to end up being 2 times 1 over 1, which is, of course, just 2. So the first residue will be 2. So this is 2 pi I times 2. And then we have to do this process again at pi. I'm sorry, add not pi, but add 2 pi and negative 2 pi. And so at 2 pi, so the residue of f at 2 pi is going to end up being 2 times g prime of 2 pi over h double prime of 2 pi. And so that's going to end up being, let's see, g prime of anything is 1, so that's 2 times 1. H double prime is cosine. Cosine of 2 pi is 1, and that's again 2. And then likewise, for the third residue, the residue of f at negative 2 pi is going to be 2 times g prime of whatever, because that's going to be 1, divided by h double prime of negative 2 pi. And that's again going to be 2 times 1 over 1, or 2. And so it turns out that all of these residues happen to be just coincidentally all 2. And this is going to be 2 pi I times 6. So altogether we end up with 12 pi I. Okay, and there's our answer there. So this integral of 1 plus z over 1 minus cosine of z is going to turn out to be 12 pi I.